remember I started with the same list, right? Self, mixed, intra. So we're going to start with the same list again and talk about some of the pieces of Claisen condensation that we should be made aware of. So in terms of self-aldol condensation, in order to run a self-aldol condensation, we run these in basic conditions and not acidic conditions. Okay? So Claisen is run in basic conditions. And when we say basic conditions, we run them in a base that matches, and we've talked about this before, but just in case we're reminding you now, we use a base that matches the OR group in the ester that's undergoing the condensation. Okay? So in this example, I would not use NaOH, that's a base, right? Not use NaOH because that's going to run a hydrolysis reaction, or the potential to run a hydrolysis reaction. So that's out. That's a no. No NaOH. Two, I can think of lots of OR bases I can use, like I can use OET, right? I'm not going to use OET because that could exchange out this OCH3 for OET. And I don't want that to happen at all either, okay? So I always use a base that matches the OR group, okay? So that's number one. So one of those, trick questions that you see on an exam or explain questions is, here's a reaction, it's run in the wrong base, what's the problem, right? So you should be able to recognize that NaOH is going to run these hydrolysis reactions. That's the problem. There's that potential side reaction. And if I use a base, an OR that doesn't match, I can get these ester switch outs, right? OCH3 for OET or OCH3 for O-propyl, etc. Okay? So once we use one that matches, we know with self-condensation that I need to create a donor and acceptor population in the same reaction pot, right? That's the requirement. Every reaction requires a nucleophile and an electrophile, right? Right now I only have a nucleophile. Once I dump in some base, I can deprotonate at the alpha site and get some population of ester that can serve, in this case, as my donor, right? So if we consider how much we're going to get, I hope you recognize it's not going to be a ton. It's less than we see in aldol, okay? Because the pKa over here is 25, roughly 20 to 25, right? So it's scaled as a sort of a broad range. And over here, this is 16, which in essence means that this reaction sits to the left. There isn't a lot that sits around that is our nucleophile of choice, right? So maybe we're at 90, 10, I don't know, I'm just making up numbers, right? Just ratioing to some extent. This being the 10, this being the small amount, right? But certainly I am going to get a small amount of donor, and our donor is always our nucleophile end of these reactions. And I'm going to have lots of acceptor, which is the electrophilic end. And again, if we focus on what the nucleophile and the electrophile are, the nucleophile is always the alpha carbon, right, the deprotonated carbon, the one that's directly next to the carbonyl. And our electrophilic center is going to be the carbonyl center, okay? So if I now condense these two on one another, so I'm just going to flip one around here to make it a little bit easier to see. Okay, I have nucleophilic attack and electrophilic center. This is what we see all the time, same thing, right? It's kind of getting a little old, I'm sure. And the direct result is a tetrahedral intermediate, and the tetrahedral intermediate has an O- that came from the carbonyl oxygen. It has an OCH3 still on it. That was the OR group from the original electrophile or acceptor. And it has the R group itself, right? So it contains all pieces that were attached to the acceptor. This becomes an O-, this is made in addition, okay? So my new bond here is this bond here. It's my new bond, okay? Now, clearly this is reversible. So I have a reversible reaction that can happen to some extent, okay? That's a possibility. Now, if it reverses, it's going to let go of what just added, right? But if it moves forward to look for something new and novel to let go, we can try losing the OCH3. Now, you can note that my arrow back, and we never ding you on the size of these arrows. I know Kim says this all the time, and I'm here telling you that as well. But you can see my arrow back is kind of tiny, right? And that's because really OCH3 is the better leaving group in these conditions compared to what I just added. Use a simple pKa comparison, right? Leaving group propensity, that's the buzzword, right? Leaving group propensity, that is a category you should be thinking in for potential exam questions. In this case, if I lose this molecule here, or this leaving group, however you want to call it, I'm going to wind up with this. And what's so special about this, first and foremost, the end of a Claisen condensation product or reaction is these 1,3-oxo groups. This is one potential product. Remember how I said when we looked at aldol, we get a beta hydroxy ketone or aldehyde or an alpha beta unsaturated ketone or aldehyde. This is the first potential product that we can have. And this is what I would call as a 1,3, I don't know if you put a dash or a comma. Maybe it's a comma. The dash would suggest 1, 2, 3. I don't know. A 1,3-oxo system. And for that, I mean if I start counting on a carbonyl and I count toward the other carbonyl, I go 1, 2, 3. It's a 1,3-oxo system. 1,3-oxo systems are direct results from Claisens. We can actually get another product. I am going to talk about that in just a minute. I'm just going to put that on hold. But this is one potential product. So if I had something on my exam, I now have two categories, right, of which I need to recognize what mechanism it underwent to get the product. I can either have a beta hydroxy ketone or aldehyde. That definitely did aldol. You should be thinking aldol. I have an alpha beta unsaturated ketone or aldehyde. I'm still thinking aldol. If I see this 1,3-oxo, I'm not thinking aldol. I'm thinking Claisen condensation. Okay? So I got to start thinking about how to pick these back apart to get back the donors and acceptors. Okay? Now, we're talking about this reaction, and certainly the OCH3 can come back in here. This is reversible to some extent, and you know that the OCH3 can react here. You've seen that, right? You've seen that reaction in the past. It would certainly react here before it would react here, because this is more reactive. It's a ketone, right? Carbonyl of a ketone. This is the carbonyl of an ester. This is another place where you could be questioned on a theory type question, things that we've talked about. Okay, does everyone understand which carbonyl would it attack? A or B? And A is the better one, like the eyeglasses, right? And that's where you would see it. But what's so interesting about this last step is that there's acid-base chemistry. These protons that are now sandwiched between these two carbonyls way shoot down to low pKa values. The pKa of this proton that I just put on the board, right, just drawn on the board, has a pKa of 9. 9. We went from 25 over here, right, to 9. That's crazy, right? And hence, you are going to see an irreversible last step here. I guess I'll just go down here. You see an irreversible last step that leads to the anion, right, being created, and that's what sits at the end of your reaction. If you were to be able to use some sort of systematic way to study what's in your reaction flask, this is in your reaction flask, okay? Now, there's a lot going on here, and a lot you can sort of talk about. I remind you that we constantly are talking about Le Chatelier's principle here. As this reaction happens, I'm going to get more and more of this, aren't I? That reaction, that acid-base reaction over here, is going to draw forward. So hence, this reaction is going to continue to happen, and there's a thermodynamic drive at the end. That's the acid-base chemistry, right? So this is what I have dominant in the reaction mixture. And what I need to do at the end of the reaction, if I want to collect it, right, is I need to dump my whole thing into a SEP funnel. I need to add an organic layer and then add acid, right? So it'll protonate this, and that'll move to the organic layer. And now I can go rotovap that off or whatever you do. I don't know. I worry about all the fumes that go off the top of the building. But regardless, this is how you would collect it, right? It would need acid workup is what I'm saying. Because this is the end of this reaction. It is an irreversible reaction because of this last step. So you need to do some workup in the end. Yes?
Why wouldn't they start attacking each other?
Why wouldn't this anion attack at the base carbonyl, like at the ester itself? Or itself in general. So what actually hinders that sort of concept is actually hindrance. Now it does happen to some extent, absolutely. There is the possibility of that, and actually some really interesting drug syntheses, which we bring in on pretty much the last day or toward the last day. I bring in some drugs that you've heard of, right, Lyrica and all these others. You can actually now see all the reactions to synthesize them, which is pretty cool. Some of them do use these crazy nucleophiles at carbonyl centers, but those reactions are needing babysitting, right? Because you got to push them forward. So the steric hindrance actually keeps it from happening pretty well. Okay, very good question though. Okay, does everyone understand what I mean? Yeah.
How is that step reversible? When you're adding the carbon or connecting
This step here?
Yeah. How is it
Because when this carbonyl collapses, right, this is a potential leaving group. This is about, I mean, it depends on how close the pKa's are, right? If this is 20, we're comparing 20 to 16. You know what I mean? It could be either or. Certainly this is being lost more often than this is, but there's some reversibility associated here. Okay? Okay. So one thing you should note about this, and we're going to do our magic workup step, right? So we're going to erase this last acid-base reaction and just talk about the product that we get. Here it is. It's very exciting. This is the product that I get from this reaction. Okay, so now separating ourselves from the mechanism, I have this product. There are other things I can do with this product, and these are kind of tricks of the trade, and they happen very often, and I'm noting it right now. I can also take this end product and hydrolyze the ester. I can hydrolyze the ester with OH minus and H2O. That would be an irreversible one, right? Or I can use H3O+. Either is fine. And all I have to do is add a little bit of heat. And this is what you're going to get. Okay? On the way to the final product, you're going to get this. And I'm sure that you can bother yourself to collect some of this if you wanted. But as you heat this up, what you're going to see is the decarboxylation. Because here you have a 1,3-oxo compound where this guy is a carboxylic acid. Decarboxylation happens from carboxylic acids that have a 3-oxo group that we've talked about before, right? If I were to name this for nomenclature, I would start 1, 2, 3, 4. It's butanoic acid that at the third carbon there's an oxo group. 3-oxo butanoic acid. When there's a 3-oxo group, I can decarboxylate, which means I can remove this whole piece here through decarboxylation. The decarboxylation is made aware to me right here. That is my sign that decarboxylation can happen. All carboxylic acids that have a 3-oxo will be gone. If I have 5 of them in the molecule, all 5 are gone. If one's there, one's gone, which is our example here. And so I'm left with a singular ketone. Does everyone see that? That I just get a ketone out of this. Okay? So this obviously is another potential end product of a Claisen condensation. So again, reviewing, aldol can go back to, or can be done to get a beta hydroxy ketone or aldehyde, or an alpha beta unsaturated ketone or aldehyde. These Claisen condensations can give you 1,3-oxos, and they can give you singular ketones that have gone through hydrolysis and decarboxylation. Yes?
How did you get rid of carbanion?
So the carbanion I did with acid workup, right?
Oh.
So since I'm on the board, I'll be able just to erase that nice little anion, right? And stick on the hydrogen there, which is just what I did. This piece here is separated from the mechanism we were showing above. Okay? Yes, I'm sorry.
The heat, does it have to be used in the second step, or can it be used?
So it can be used in a second step, and sometimes you see that. I mean, I'm just saying as you hydrolyze and heat, you're going to begin to see this. But yes, it could be either together in separate steps. Oftentimes you see it in separate steps. I see that as well. I don't think that necessarily means you react it and then heat it. I think it means you can dump everything together and then go reflux it. You know what I mean? I don't know if they're like 2 distinct steps necessarily. Yeah. Okay. Yes?
How do you go from ester to carboxylic acid?
So an ester to a carboxylic acid is the hydrolysis reactions that we learned in the last chapter. Okay? Does everyone understand what I mean here? Yeah.
If you have like a carboxylate, can you
the end, I can't, because a carboxylate is generally created, right, in OH minus and water. And water alone is enough to actually create now the neutral carboxylic acid, which is what's happening, okay? So we show the carboxylate, but there is still some neutral carboxylic acid that's there, small amount. Yes?
Won't the OH attack the center on the right?
Okay, so the OH minus can attack the center on the right, but what we've learned, and one thing that I've been trying to hammer home, right, is we don't actually see those hydrated complexes, right? If OH minus does add, it's not going to stay on, it's going to fall right back off. If you study the equilibrium studies of those systems show us that it's the keto side that is dominant in solution. Not to say that, you know, everything's in flux and everything's happening. Not to say it can't add, but it's going to come right back off, because that's not a favored product. Okay. Yeah? Oh no, you can collect this. I was just saying on the way to, yeah, so that's why, that was my box. On the way to grandmother's house, we get to this meeting. Yeah?
If the ketone is an acid and you heat, what's gonna happen? The box.
The box.
If that's an OH on the right.
Oh, if this was an OH on the right, I'm going to get an OH here. I can only lose one, right?
One time.
One time, yep. Because once one leaves, I don't have a 3-oxo group anymore for this to be gone, right? So only one can leave. That's a very relevant question. Relevant to the homework. I like that. Okay. I see exactly where it is. All right. Is everyone okay at this point? Okay. So to save a little bit of time, I'm going to talk through the mixed approach just very quickly. We are going to do some retrosynthetic analysis here in just a few minutes, so we're going to see some of these. But there's also the ability to do these mixed approaches. In the mixed aldols, we talked about creating an anion that we made with LDA, and then we added some acceptor molecule, right? We don't have that problem so much with Claisens because there's only ever one beta site, right? I mean, one alpha site that can be deprotonated. So oftentimes, just in a timed manner, you can run these reactions very simply, but LDA certainly can be used, okay? So my point here is that I can take an ester of any variety and add a base. Add LDA, that's fine. LDA is sterically hindered. It's not going to do anything but behave as a base, okay? So LDA would be a fine choice here in a mixed approach. I think that saves you a little bit of thinking, right, when it comes to studying for the exam. Because a mixed approach can use LDA at any point in time, okay? The second ester that I add actually can either be of two varieties. One would be one that I don't ever have to worry about there being any deprotonation at the alpha site, right? These are molecules that can only be acceptors, okay? That's a very, you know how the exams start with very simplistic questions up front? This is a very good simplistic question up front. Which of these esters or ketones or aldehydes can be donors and acceptors? Which can be acceptors only? Which can be donors only, okay? This here is an example of one that is an acceptor only, right? And this here is one where it can be a donor as well. But because of the progress, the methodology you're using, you created the ester enolate first, and then you're adding this. There's no worry about this ever being the donor in your reaction. It's the acceptor because of the methodology you've used. You've taken an ester, you've added a base, you have your ester enolate. That is your donor. If you add in your acceptor slowly, the acceptor will never become the donor because you have a huge population of donor in your reaction flask waiting for the electrophile to be added. Okay? So in a time sense, we don't need to worry about that. Okay? Everyone understand that? The last thing I want to say about these mixed is oftentimes things are really mixed, which means I take an enolate, not an ester enolate. This is an example of an ester enolate. It's what we call an ester enolate. This would be an example of an enolate, comes from a ketone or an aldehyde. Okay? is a difference, ester, enolate, enolate. I can actually create an enolate and react it with an ester. Those are still considered Claisens. Very odd, but they are, okay? So I can take an enolate and I can react it with an ester as an acceptor. So really we've crossed the Claisen aldol line, I realize, but those are still considered Claisens, okay? We're going to see that in our retrosynthesis. So I want to kind of skip through the mixed line and just talk about a couple of these intramolecular reactions, okay? The first one I want is for you to try on your own. We're going to compare, we're going to compare two intramolecular Claisens. You know I sort of like these questions because they're thinking questions, and I'm trying to get you to see the material, you know, in its specifics as well. So if I take these two molecules, actually, no, we can take let's do just one. We're going to do just one. Okay, I think that's going to be better. So here's my one molecule, change the tune here, and I can create two products from this one molecule. Two products from this one molecule, okay? Remember, what you need to do is add some base to match the OR group. So in this case, I'm using ethoxide, not methoxide, because it matches my OR group. And now I have to consider the two potential alpha sites that can be deprotonated. Everyone recognizes that they're different from one another, okay? So that's important. So I can cross, as we've been talking last class, right? We were talking about these intramolecular reactions. I can cross B as a donor to G as an acceptor, right? I can cross B as a donor, so I generally will call this a BG cross. That's what I'll do, always starting with the donor and going to the acceptor. But that molecule is, in essence, this nucleophile and this electrophile being crossed. Okay? Can you draw a product that shows that cross? Sort of got a little smudged. I'm just going to add it back so it's clear. So this is what you should get on the right board there when you cross those. Okay? You should get that directly out as a product. You should create a 6-membered ring. Remember, you can be logical about it. Count the number of carbons that intervene between your nucleophile and your electrophile. So 1, 2, 3, 4, 5, 6-membered ring. Okay? You can letter it all. I stopped lettering it, didn't I? So you can letter it all. A, B, C, D, E, F. That E was for electrophile. It's actually G. The E there before was standing for electrophile. Okay? And so in this case, then, I have this cross. Okay? Yeah.
Isn't there supposed to be an OET coming off of G?
Off of G. So G loses its OET when it's the acceptor, right? So when it's the acceptor, the tetrahedral intermediate collapses to drop off this. So the acceptor always loses this piece, always, okay? It's kind of some trick that you can use to get faster at these. That's exactly what happens, okay? I can also have an F to A cross, right? Does everyone see that? I can have an F to A cross. And an F to A cross means that A is my electrophile, okay? That's A. And it means that F here is my nucleophile. my nucleophilic atom here. Okay? And you want to draw up a product for that. You can show your F to A cross. Okay, yeah. Okay, I'm about to ask you that. Great question. You can write my exam. That's good. Her friends are rolling their eyes. I don't know what that means. Okay. Which one is favored? Can you give me a good argument? Yeah. Okay, it would be the first one. The anion is not more or less stable. The anion can be formed over here. Does everyone see that this, it's very, very small detail. Does everyone see that if I focus on the carbon between the carbonyls, I can have an anion there. Can I do that here? No, I cannot. So which reaction is more exothermic? The one on the right, okay? The acid-base chemistry is what drives this reaction forward. I didn't show the mechanism, but you know the last step is deprotonation of that center. Yes?
Oh, no.
Okay. Yes?
Does it not matter at all, like, which anion would be more stable in, like, the beginning?
Okay, now that's also a great answer, and I'm likely to give you credit for this thinking answer as well. So what would your answer be? What would you say about F and B? B would be better because it's a more stable carbanion. Also a great answer. Okay? Okay. Yes? Because when all is said and done, there is a hydrogen that can be deprotonated here, whereas over there, there is no hydrogen. And the last step in all of these is the deprotonation of the carbon between the two carbonyl centers. That's what I'm really trying to get you to focus on in terms of the exothermic drive for this reaction, right? It should be Thursday, like Throwback Thursday. What was the exothermic drive for aldol? Conjugation, the creation of a conjugated system. That's exactly right. That was the thermodynamic drive for aldol. You know, Jessica, where are you? There you are. I was talking about you in my 231 class today. Because someone used something I did not even know what it meant, and I was like, yeah, okay. Someone was in my office yesterday, Jessica was in my office yesterday, and she was trying to throw out all these new wave terminologies that I know nothing about, and they got such a kick out of me saying turnip because I don't even say it right? Yeah, I say it like the root vegetable. And it's supposed to be like, I don't know, how are you supposed to say it?
Turnip.
Okay, there you go. I'm going to get better at this. You wait for the final, man. Okay. So I was talking about you, and they got such a kick out of that, and I'm like, yeah, you should know Jessica. She's very nice. I even spelled it properly. Okay. So this is an intramolecular example. So what I'm going to do is clear the board, and we're going to put on two products, and we're going to try and work backwards so that you can do that as well. Right? Here's product one, so as I erase, you can work on this.
Yay. As in
And here's product two. So here we go. See if you can come up with the donor and acceptor that we use to create each of these. Okay, let's start with the more obvious one. The 1,3-oxo is obvious, right? 1,3-oxo is definitely a Claisen. We have no trouble with that. We should be able to see that for what it is. Okay? So the Claisen here could have been made for two different potential starting materials, right? Paths, I should say. Because you could have done, right, this bond could have been made, or this new bond could have been made, right? So you could write out two potential paths and make an argument for one path over the other, okay? So if this is my new bond, that's how I would consider it, right? If this is my new bond, A, path A, that therefore I'd break this bond back, right? I'd turn them back against one another. I could have started with this as a donor, and this guy, and I could have OCH3, OET, go crazy, okay? I could have O whatever. So this would have been my donor here on the left. You can keep it with a negative charge on it if you like it that way. I'm totally fine. You don't need to deprotonate, deprotonate it back. And this is your acceptor. Everyone see that? Or if I had B as my new bond, I would have broken it the other way, and I would have had something like this. This would have been my donor, and this here could have been my acceptor. Does everyone see that? Yes? All right. So you can make an argument for one or the other. Yeah. I don't really think there is a big difference. Obviously, on your exam, there would be a pretty big difference. But no, I mean, you have a good carbanion either side primary, right? No issue there. No ability to deprotonate on this side, so really only one in each case. And the acceptors, I mean, this acceptor is probably less sterically hindered. That's probably where I go. That would be the most obvious answer. Okay? Is everyone okay with this? Now, this is called a Claisen, but you can see we're not using an ester enolate, right? We're using an enolate, something that's created from an aldehyde or a ketone that was deprotonated, and then we're using the acceptor ester molecule. Okay? Everyone see that? It's classically mixed cases. Okay, so what do we do with this ketone here? This is the sort of driving force back. You need to recognize that you lost carboxylic acid, right? So you need to add in a 3-oxo group. So here we go. I'm going to add it back in. Does everyone see that? I now have a 1, 2, 3-oxo group, right? It was a carboxylic acid. I've gone back one more step to the ester, right? I've gone back even one more step to the ester, and this is what I get. So the question is then, what's the new bond? The new bond isn't a dual choice here. There's really only one new bond, okay? It has to be, right, this bond here. This bond can't be a new bond, okay? So this is my new bond. I can break these two pieces apart. The carbonyl side was obviously my acceptor side, my electrophilic side. So as I come back, I'm like this. So this is my electrophilic side. The carbonyl side is my electrophilic side. My electrophile has to be an ester, right? So I've got to add an ester back. And my donor side is the non-carbonyl side. So my donor, just to keep it in the same sort of way it looks now, is this guy here. Okay? This is my donor. Okay? So I have an acceptor and a donor. So the strategy here, okay, is to add back the group that you know you lost, which is the COOH, making sure to add it back as an ester, okay? And then work through. Yeah?
Why can't that be an alpha beta unsaturated organic?
Why can't it be an alpha beta unsaturated and then use H2 platinum? Is that where you're going with this?
No, I'm saying that the bond was formed a double bond.
Oh, you don't generally see that. Although that's smart, sure. I mean, I guess you could, but no, that's generally not something you see. Yeah. Benzene usually stays an intact unit. I get what you're saying. There'd be a huge driving force for that, wouldn't there? Because you create this aromatic system and you're like, whoa! Yeah, I get you. Yeah.
So just for clarification, can you clarify as to why the other bond can't be broken?
So this bond can't be broken here. Okay, so this is a no, right? Because how would I create an anion or a donor from this carbon here, right? Do you see what I'm saying? Yeah. So I can't create a donor on either side. So this is not my new bond. Okay? That's a good question. Again, I put an X through it, and I want you to think about it, about creating a donor on this side. Can't do. Okay? Meaning a nucleophile. Yeah.
So are we just like, how are we supposed to assume to add back like the ester? Like, I know now we're talking about it, so it was kind of like when you said it was obvious.
Yeah.
But on like a test or something, how do we know like to like think about that?
Okay, great. So I'm trying to give you the how-tos, right? So there'll be this section on your exam that's going to say, show me, the donors and acceptors that are used to create these products. Okay, you actually have a problem like that on your homework, right? Just like you'll see on the exam. And so you look at them, and we've already killed what comes from an aldol, but I'm telling you, what comes from Claisen is going to be 1,3-oxo systems and singular ketones. Singular ketones, you employ this strategy, right? You go to the alpha site. Now, sometimes there could be 2 alpha sites. There is not in this case. Sometimes there could be 2 alpha sites, and I add back. I can't go to this one you recognize because I can't put a bond there. But if you could, because it was a linear system, you can certainly do that. Yes?
Can you explain why you added that other guy?
So I added the ester because if it's a Claisen reaction, right, I need a nucleophile and an electrophile, right? I can see that this was my electrophilic entity, but I need to be able to make a nucleophile. And the only way I can make a nucleophile is if I have an alpha site to deprotonate, right? So I don't have one right now. Yeah.
Why can't you make that alpha carbon the nucleophile?
So in essence, I guess you could do this sort of thing. That would be sort of cheap. But yeah, okay. I see what you're saying. You want to do something like this.
Yeah.
Yeah, sure. Go ahead. That's all good too. Yes. Yes, that's totally fine. I'm with you now. I wasn't sure where we're going with this. But I now am with you. Okay.
So
all right.
we can now break that
So
up?
think about how to go back and start with that electrophile. Okay.
What?
You can use it. Yes. Yes. Yes.
If you use that as the electrophile, that wouldn't kick off the ester and you couldn't get rid of the acid.
So if you use, no, I think it would work. We can try it. Let's see. So if we went the other way, what big hub is now, let's see. I go through my X path, I have this, and I would need to use some crazy thing that's large. Hold on. So we'd be something like this. And this. Okay? But in this case, you can't have that, right? There has to be 2 OETs because I need a leaving group. So we're going to change that. I see that now, and as you were talking, I was seeing it. So now, if I cross these guys, which we're about to do, this is my acceptor. Obviously, can only be an acceptor, right? This is my donor. So I'm about to cross them. Nucleophilic attack. Cheating here. That's a total cheat, my mechanism, but we're cheating. So we're okay. Okay, and now I get this guy out. Now, what's the difference between my 2 reactions? We are getting the same products. I totally agree. Okay? But let's just come back and be thinking about it. What's the difference between these 2 reactions? Which one of them is going to be easier? Yeah.
Is it the first one because of the stability of the negative charge on the carbon?
Okay, so So you have a primary carbanion there. Absolutely, I think that's a very good thinking answer. Can someone make an argument for this side here?
Secondary.
It's secondary.
Oh, is it secondary? It is secondary. I didn't see it either. Okay, secondary, yeah. Okay, this ester is not reactive. Why? Great call. What makes this ester less reactive than the one on the left side? It's not the symmetry, although it's related to the symmetry, yes. What do these OR groups do? They donate electron density in. So I'm donating electron density in from two ends here, right? So this is not good. Someone want to make an argument for this carbanion, the ease of making this carbanion compared to that one? Wouldn't this pKa be lower? Yeah? Than that one on the left board? Because it's 20 to 25 for the ester enolate, 16 to 20 for this ketone. Okay? So that might be an argument. There's lots of factors that influence one another, and it really, really depends on what you have as starting material and what you can do. Sometimes you can only use one path as a building block, and you're forced. And you're forced to make it work, and you're forced to get it to go in a certain direction. Okay. All right. So we're going to spend the last 10 minutes building up the Michael addition piece of the back end of this chapter. There are a few other things we need to talk about, but I'd say this is probably the last big hurdle in this chapter, and that is Michael addition. Okay? So Michael addition only occurs with alpha-beta unsaturated systems. I'm starting with a ketone or aldehyde, you can see. Today, I'll pretty much be talking about ketones and aldehydes. But I can have alpha-beta unsaturated esters, alpha-beta unsaturated acyl chlorides, alpha-beta unsaturated amides, etc. Okay? And there's a little bit more thinking we have to do with those reactions because we have to consider the reactivity of the carbonyl compared to the reactivity of a secondary electrophilic center, which is this electrophilic center here. Okay? So this is an electrophilic center that I would consider soft, fuzzy, diffuse, not necessarily as good as this obvious electrophilic center, which we have focused on almost exclusively since we started our ketones and aldehydes chapter, right? So these alpha-beta unsaturated systems lend themselves to another electrophilic center that can be created, and you can see it through resonance. Through resonance, you can see that this center here becomes a secondary electrophilic center. Okay? And so with these systems, we have to worry about competing reactions. As we can see with many of these systems that we've talked about, right? There's all sorts of competing reactions. So the two competing reactions that I need to worry about with these systems are as follows. The first would undergo what we would call a direct addition. This is exactly what we've been talking about since the beginning of the term. A direct addition would be taking a nucleophile that's going to go right for the carbonyl center, okay? And thus reacting at that site. So it's either called direct addition or sometimes it's called 1-2 addition, okay? But more often than not, I think it's called direct addition. That's attack of the nucleophile right at the carbonyl center. There is a secondary competing reaction that only occurs in these alpha-beta unsaturated systems. It has to be an alpha-beta unsaturated system, not a beta-gamma unsaturated system. Just to be very clear, a system like this does not have competing direct and conjugate additions. Because this is not an alpha-beta unsaturated system. It has to be alpha-beta. count of the systems. It just comes from like a count where we start at the carbonyl oxygen as number 1, and we count through the double bond. So 2 would be 1, 2 would mean the nucleophile is adding directly to the second carbon. 1, 4 is saying the nucleophile is going to add to the 4th carbon. Okay? So conjugate addition works something like this, where I see direct attack here at the 4th carbon. Okay? It's literally attacking a pi bond, right? Very odd. Very odd. And we can't keep 5 bonds there, so we have, in essence, pass off, bless you, to create the enolate, in this case, right? This is an enolate, and these tautomerize as they always do, right? In essence, to give me back my intact carbonyl. Yes?
Do you need heat to run these?
Okay, now there's many features here. Sometimes you do, and sometimes you don't. That's probably not the answer you want. No. That's the answer that we're going to go with, because it really depends. Okay? We're going to start talking about the dependencies we have here. But what you should note is, here is your new bond. It's between the nucleophile and carbon 4. The double bond of the alpha-beta unsaturated systems removed in conjugate addition. The carbonyl remains intact. When we're talking about direct addition, my new bond here is where we expect it to be, right, to the carbonyl center. The carbonyl is removed. There's no more carbonyl carbon here, right? Generally get these alcohols here, and the alpha-beta unsaturated double bond, the double bond that was present, still exists. Yeah?
So how do you move that reaction forward? Like, isn't the conjugated
Okay.
way more?
So that's a great question. Now, there is competing sort of concepts here. There's going to be a bunch of different mitigating factors. But we can go back to this idea of heat. So we're going to go back to talking about which one of these is generally favored and why. So, could someone use that knowledge? This would be the 3rd time we've seen it. So this is the 3rd time we've seen this concept in Orgo 2. So if you don't expect something like this on your final, you're all not thinking clearly. Kinetic and thermodynamic. Can someone make an argument for me on the board as to why direct addition might be kinetic or thermodynamic and vice versa? Yeah.
Thermodynamic, because it would create the more stable carbanion.
Okay, it's not about carbanion stability, but I like that. It's still going to be considered thermodynamic, though. Why is this going to be considered thermodynamic over here? What do we keep? The carbonyl. What element is more stable, a CO double bond or a CC double bond? CO. CO double bond is more stable. The evidence for that is in an IR, right? The CO double bond has a wave number peak that is higher to the left, higher wave number than the CC double bonds. Evidence for the strength of the bond. The CO double bond is stronger. On the left, we see a kinetic product because the better electrophile is reacting. The better electrophile is reacting. Okay? But this isn't the only thing we have to think about. There is a lot of thought to what types of nucleophiles are going to undergo direct or conjugate addition. Okay? And that's where we're going to start on Monday. What nucleophiles do direct? What nucleophiles do conjugate? Okay?